All right, so I wanted to get back on to the mineral piece of the conversation here today, or this section of the day. We did cover water to some decent degree, I believe, already, and I don't have a lot more to say about water. Feel free to bring up questions if and when you feel so inspired. There are page 2 and page 3 and page 4 and page 5 are, if you haven't figured it out yet, are in many cases not ordered properly. So make sure you figure out which pages are where. We're going to go through a number of pages here between now and lunch. And also we're going to be reading this this report here. So make sure you got the Sawdust report. I would like you to be able to read this fairly well by lunchtime, and it shouldn't be too hard. Make recommendations for yourself based on the Sawdust report. Not that big a deal. Before I go into it too far, I want to do some basic background, and I'm going to erase some of this too. All right. So then we had a small comment during the break about remineralization. My entree into this whole world came through the remineralization perspective. John Hamaker wrote a book, Survival of Civilization, was it the name of his book? Something like that. Yeah, I think it was Survival of Civilization, but so just to step back for a second here, we have this concept in history, at least in the West, in agriculture, as something that started off 10,000 years ago, 8,000 years ago, something about the Fertile Crescent, Mesopotamia. People have this somewhere, vague recesses of memory. High school, which was more or less distant, depending on who you are in the room. For some people, it's not that distant yet. Others of us, it's actually getting to be somewhat distant. I was speaking at a university, I'm not sure when it was, this winter at some point, and I realized, oh my God, these kids are half as old as me. Like, I've had half of my life since college. So I was like, whoa, I am maybe getting a little bit old. Anyway, older. Or something. There's got to be another way to frame that. I actually got a degree in history at university. That's what I formally studied. If you look at history and you look at sort of major agricultural civilizations, and you look at the ones that are still around and have been doing agriculture in the same spot for thousands of years. We got lots of places where there were civilizations and there's ruins and there's nobody there anymore, where it's desert. And we got a few places where there's still people and big cities and cultures that are thousands of years old that are farming in the same spot. And there's only a few examples of where there's still big civilizations that are thousands of years old that are farming in the same spot. And I think of the, besides the Tigris and Euphrates River Valley, which is there are still ancient cities in the same spot that have been going for a long time. We've got the Nile River Valley, we've got Egypt, we've got the Indus and the Ganges River Valley, you've got the Indian culture, and we've got the Yangtze and the Yellow River Valley, the Chinese. But nowhere else do we have agricultural civilizations which have been doing agriculture and maintaining civilization in the same spot for thousands of years. Everywhere else, civilization has come. Cities came, wars, and then now we've got cities in the middle of the desert. You look in South America, the Incas and the Central America. You look in, parts of the Middle East. You can look in Africa. There's these ancient civilizations that rose and then fell. And John Hamaker put forth this idea that part of the process of agriculture is when you are harvesting crops off the land is you're actually harvesting minerals out of the ground that if I'm harvesting off 20,000 pounds of crop per acre per year, most of that is carbon and oxygen and hydrogen and nitrogen from the atmosphere, but some percentage of it, 500 pounds, 1,000 pounds, 1,500 pounds per year, is minerals from the soil. And the plants are trying to put into their seeds the most critical nutrients for next year's generation. And so when we keep harvesting those seeds off the soil, we're actually mining the soil for some of those critical elements that are needed for biochemical reactions, for enzyme system function and the DNA and all that kind of stuff. So functionally, in many cases, the process of agriculture over time, over decades, over centuries, over thousands of years, is a mining process that wears out the land, especially when you're doing tillage. And so what happens in these river valleys that keeps them able to be doing agriculture for thousands of years is the annual flood. If you look at the Nile River Valley as an example, you've got the Blue Nile, which comes out of the Congo, which is a jungle like the Amazon, basically, massive, amazing jungle, and that's full of organic matter and life that's coming down in the spring flood. And the White Nile is coming out of the mountains of Ethiopia, where they've got glaciers that are grinding up the rock. And so the White Nile takes all the crushed up rock dust, and the Blue Nile takes the organic matter and the biology, and they mix, and then that gets spread out over the land, and you're able to do amazing agriculture in that same spot for thousands and thousands of years, because whatever's being taken out is being put back in on an annual basis. I can't remember, it was Palmyra that the Syrian army just took back from ISIS a couple weeks ago, what they call a desert city. There's an ancient city there which is surrounded by desert. It didn't used to be desert. They didn't build a city in the desert. They built a city in the rich plain, and then they practiced agriculture and wore out the land, and now it's desert. Right? You can look at a lot of places on the planet where there used to be rich land, and there's big old cities that used to be there, that the residue of them is still there, and it's desert. And it's because agriculture practiced the way we practice it generally wears out land. Right? There used to be 40 feet of topsoil in Illinois, now there's 4. Lots of places in Minnesota, they're down to the subsoil. They're down to the, to the rock. The soil's all gone. The dozens of feet of topsoil that were there are no longer there. It's all down the Gulf, exactly, right. Along with the fertilizer, which is creating the dead zone, which is, anyways.
I just learned that this area originally had like 16 feet of topsoil in the Piedmont.
Yep, absolutely. So that form of agriculture that we're talking about, that we call agriculture, which is tillage, whether it's with a simple wooden plow and or whatever, and grain, and which is a monoculture, is a way of agriculture that wears out the land. What the Native Americans are doing here was a whole different kind of agriculture that we don't even recognize because it's so sophisticated, because they didn't have any beasts of burden, they didn't have any machinery, they didn't have any wheels, they didn't have any plows. They were working much more sophisticatedly with nature, and they were actually building soil. So that's a whole different kind of agriculture, which is what the permaculturalists are trying to talk about. And people are like, oh, you guys are permaculturalists, you don't know what you're talking about. But I think there's a lot of wisdom in that. It's a whole different version of agriculture, a whole different vision of agriculture. People may have heard of this book, Restoration Agriculture. Anybody heard of that book, Restoration Agriculture? Mark Shepard is a farmer from Wisconsin, I think. And he does the math on, the land of milk and honey. The land of milk and honey is where you've got lots of bees making honey and lots of cows making milk, right? You've got, in the Bible we have the land of milk and honey. The land of milk and honey, he says, is a savanna ecosystem, where you've got occasional large trees with grasslands underneath, with berries and nuts and brambles, and sure, plenty of annuals as well growing. He does the math there on how many calories you can produce on an acre, of what quality in this book, and he lays out how categorically you just blow conventional ag out of the water with a savanna ecosystem, which is basically what the Native Americans were running across the majority of the continent, was a savanna ecosystem. They were managing it for that model, and that was building topsoil, that was building soil. So I didn't talk about the carbon sequestration. I talked about how 40% of the carbon in the atmosphere that's been added since 1750 came from the soil. I didn't talk about how plants actually build carbon. I'll just get that out of the way. It's a tangent, but I want to cover it. This process of water plus carbon dioxide plus sunlight being turned into sugar and oxygen. The oxygen goes into the atmosphere, that's what we breathe. The sugar, in majority, goes into the soil. There's carbon from the atmosphere going into the soil in this equation. What are you smirking about?
It's just amazing that we didn't give it to recently. Or some of us.
Where did the 40 feet of topsoil come from? It came from the air, right? So we've got farmers in North Dakota, in Australia, all over the planet, operating on thousands of acres, not hundreds of acres, not single acres, not mulching and composting, farmers, real farmers, on thousands of acres that are increasing organic matter levels 0.5% per year, among many others. 0.5% per year. You figure out how much carbon is in 0.5% organic matter, and you multiply that by 7 billion, which is the number of agricultural acres on the planet, and it would take 3.5 years to sequester all the carbon that's been added to the atmosphere since 1750, if we performed agriculture well. Right? There were 280 ppm CO2 in the atmosphere in 1750. There's 400 now, 120 increase. 3.5 years, we could sequester it all through agriculture if the world's agricultural land was being managed biologically, if plants were healthy, and as part of that process of being healthy, we're feeding the soil. When you put fertilizer into the ground, soluble nutrients, that's like an IV drip direct into your bloodstream. That's like Gatorade. That's not food, right? The biological system in your gut is not being fed when you're on an IV drip. You can be kept alive when you're on an IV drip, but you're not using your gut to digest your food as nature made it. So when you add fertilizer, you short circuit the process and you prevent this process from occurring. If you have healthy plants, which I haven't talked about yet, the full implications of healthy plants, what happens is they are indigestible to fungi. They're indigestible to insects, and then you obviate the need for fungicides and insecticides, etc. Yes?
Can you just do the run through of that equation on carbon sequestration again? I know it was
the basic process is this, and
I meant the thing that started with 0.5% 3 years.
If you so basically, we've got enough documentation and enough continents of real farmers, quote unquote, thousands of acres farmers doing this 0.5% increase per year. So that means you start at 1%, you go the next year you're at 1.5, the next year you're at 2, the next year you're at 2.5. And Gabe Brown is somebody who started off at 1.5 and now he's at 11 in the past 20 years or something like that. And he's in North Dakota. He's operating 5,000 acres. There's a woman named, what's her name, from Australia? Christine Jones. Christine Jones from Australia has been doing a lot of work down there with 20,000 acre farmers and doing some of the really simple stuff, simple stuff, and increasing organic matter again, 0.5% per year, year after year. There's somewhere between 6.5 and 7 billion acres of agricultural land on the planet, according to the UN. And so if you figure out how much carbon is in 0.5% of organic matter, and you multiply that by 6 or 7 billion acres, you see how much of that is, and how much carbon's been added to the atmosphere since 1750. It's a simple math equation. It's actually Alan Yeomans' son, I believe, wrote a book called Priority 1, where he does the math out in this.
Sorry, so PA is the key line guy. Alan is one of the sons.
PAA isn't Alan? PA?
Percival Alfred
okay.
P.A. Yeoman.
is the founder of the key line.
Okay.
I think that Alan is the one that he was talking about.
Sorry.
Yeah.
That's entirely possible. I've got the book. Usually when I drive to my presentations, I bring a whole big library of books, and then you can look at this and look at this and look at this, and I just didn't drive here. What's that?
I said I almost loaded up a bunch
You
of books
almost loaded
right
up the
out
book,
there.
yeah. Tomorrow we might have more books. Anyway, that's my understanding of the math on a basic level. Tangent, but anybody who's a big global warming, hoo-ha kind of person, you know, and they're fighting ExxonMobil and everybody else. You know, it's like fighting Monsanto. I'm like, if you want to fight, knock yourself out. My thought is that we build solutions, and the way we solve this problem is by growing healthy food. So what we really need to be doing is talking to people about how what they're feeding their children is causing them to be sick, and if they could choose the food that tasted good, their children would eat it, and then they wouldn't be healthy, and they'd be sequestering carbon, and they wouldn't need agribusiness, so then they could be fighting Monsanto at the same time, if you want to. For me, this is a much more systemic, holistic, creating the solutions mode as opposed to fighting mode. I think it was Mother Teresa who said, I'll never attend a march, you know, an anti-march. If you want to work towards something, I'll be love to be there, but don't ask me to fight. I don't, you know, you're going to push your energy against something, or you're going to put your energy towards something. It's a bit of a conceptual, you know, shift, but I think really what we can do is create solutions. Anyways, yeah.
Be an angel and don't swing your fists.
Be an angel, don't swing your fists. There's all kinds of good ways of saying it. That's not a bad way of saying it at all. Yeah, that's exactly it. Great. Okay, so I laid out the basic idea here about remineralization and the concept that you need basic minerals. This is something I did not learn about as a farmer, you know, in the organic community. I want to teach you how to read a soil test so you can make some, you know, mineral balancing decisions yourself. I'm going to give you a rationale behind what I'm teaching you to start off with, and then you can do with that as you wish. So what I'm going to teach you how to read a soil test is what's called an Albrecht-style soil test. Albrecht was he was a scientist. He grew up on a farm in Illinois. He was a farm boy, but he ended up running the soil department at the University of Missouri for 20 years. You guys have Virginia Tech, I believe. Is that your land-grant university? We've got UMass.
Tech and University of Virginia.
Virginia State?
Yeah.
The one that does all the
Virginia State.
VSU.
VSU.
All right.
Tech does
When
the
people
soil
go to
test.
when people go to study agronomy, where do they go?
They go to either school, but
Either
Virginia
one.
State's the one that-
Okay, fair enough. We've all got our own systems. It's Cornell in New York. It's UVM in Vermont. You know, in Missouri it was University of Missouri, and Albrecht was the head of the soil department at the University of Missouri for 20 years. So he's a quote unquote company man, right? He's a part of the legitimate institution. He's a scientist, which is why I like to hide behind him when I'm talking about all this stuff, because you know, he ran the university soil department for 20 years. Albrecht did his grad research. I'm not sure if it was his master's or his PhD or both, looking at a very interesting factoid, which was he was overlaying World War I draft records with U.S. Soil maps. Really interesting. He saw that the percent of boys that were accepted for the draft from Illinois was dramatically higher than the percentage of boys accepted who were drafted in Alabama and Arkansas. That the boys who grew up in what we call the breadbasket were accepted at much higher rates than the boys who grew up in Appalachia. The way it was determined whether you were fit to be cannon fodder or, you know, whatever, machine gun fodder or chemical weapons fodder, was whether you had good teeth and good arches. Because in the Civil War, if you couldn't march 20 miles and eat hardtack, you were going to get in the way, right? World War I, they didn't realize everybody's going to be stuck in a trench, so they had the standards from the previous major war, which was you got to be able to march and you got to be able to eat hardtack. And so if you had flat feet or bad teeth, you weren't accepted. Just like a horse. You got bad feet and you got bad teeth, you're no good. And the boys that grew up in Appalachia had flat feet and bad teeth, and the boys that grew up in the breadbasket had strong arches and good teeth. And Albrecht said, I wonder why. Were they all Germans over here and all Italians over there? No. No, they weren't. The Germans went everywhere, right? Where they, you know, it wasn't their genetic lineage. It was really clearly the soil type in the area where they grew up. Very interesting. And so we said, this sounds, I'm going to study this.
And
And-
where they had done a lot of rapid
Well, where we got worn out, weathered soils is where we have boys with flat feet and bad teeth, right? Buck teeth. Anybody know about the archetypes of Appalachia? And then they pushed them back.
Yeah.
Yeah.
And it's damaged. Whole jaw, everything. Yeah.
So the idea here basically is that
My mom cooked boxed mashed potatoes. And microwave, everything. So.
we are. I mean, if you understand Albrecht's work, and his contemporaries were Weston Price. People know about Price. You know about Pottinger, Pottinger's cats, right? I mean, they were figuring this stuff out a long time ago. This is the 30s and the 40s. This is a long time ago when they're figuring out that what you eat has a lot to do with your physiological development. They were feeding, Pottinger was feeding cats. They've done this with pigs. They've done this with rabbits. I mean, Albrecht did it with rabbits. He was able to get, so I'll just go the whole story. Sorry. So Albrecht took clay and he put it in a centrifuge and spun out all of the cations that were attached to it, all the calcium, all the potassium, all the magnesium, spun it all out until he had pure clay. And then he would add these cations back in different ratios. So he would do 50% calcium and 10% magnesium and 5% potassium here, and 60% calcium and 15% magnesium and 5% potassium there. And he'd do these pot tests, and he would grow out crops, seeds, wheat and barley and everything in these different mineral levels and ratios. And then he fed those crops to animals and watched the effect on the animals through multiple generations. Really thoughtful, really interesting. 500 plus published papers, right, by this guy. You've never heard of him, most of us, never heard of him. University land-grant researcher. He was able to get rabbits who were fed crops grown on good soil to increase their body weight, get larger in 1-2 generations, to get larger litters, to get longer lifespans. He was able to get rabbits fed crops grown in imbalanced soils to get smaller in 1 generation, to have smaller litters, to have shorter lifespans, right? Absolutely, totally impressive results, showing that the mineral levels and ratios in the soil had a profound effect on the physiological development of the animals who ate those crops. I think this is amazing information. It's ridiculous that no one knows this kind of stuff. No one knows any of this kind of stuff. What happened was after World War II, when the armaments industry had lots of factories that had been used to build, to make explosives and chemical weapons, and there was no market for all those products anymore, they said, who can we sell these things to? And they said farmers, and so what was a chemical weapon, a nerve gas, is now an insecticide. What was an explosive is now a fertilizer. And they basically said to UVM, they said to Virginia Tech, they said to Rutgers, they said, here's $5 million. I would like you to hire this guy and fire that one. And they systemically went through the land grant system, and people who were going to recommend fertilizer and chemical weapons were given endowed chairs and what do you call it when you can't get fired? Tenure. Yeah. You can look at the history. It's pretty categorical. It's this is just simply the facts on the ground, ladies and gentlemen. Deal with it. But what we call conventional ag really is only 60 years old, right? Conventional ag, like this is the way it's always been, is really just since World War II. The USDA, the land-grant universities were doing some amazing work in the 30s and 40s. Really, really amazing stuff, as they was envisioned in the 1860s, right? As was the idea behind the land-grant universities. So, anyways, I don't recommend the use of a land-grant university soil test because they don't use the Albrecht base saturation analysis for assessing soil. They use what's called a SLAN model, sufficient level of available nutrients. And the available nutrients they're talking about are nitrogen, potassium, and phosphorus, which are the ingredients in explosives, which if you've got present in soluble in large quantities cause plants to grow really rapidly, but to grow weakly. And when they grow weak, then nature says you are not fit for reproduction, and then the insects, which is nature's garbage crew, comes in and kills them, or the fungus, or the bacteria. When something's growing weak in a weak manner, nature says you're not fit, and she comes in and cleans things up. That's how I see it. I think there's a bunch of science that could back it up if you'd like, but we don't need to go there if you don't want to. Anyway, A&L, which some people know about, which I think is around here somewhere, used to be called A&L, is not called A&L anymore. Waypoint is one of a few good Albrecht-style labs in the country. I have a report here from a place called Logan Lab, which is in Ohio. I like them because I can get things like cobalt and molybdenum and selenium and silicon, along with about other 14 elements for $30, which is the best price I've been able to get for so many nutrients. So we have Logan's form available on our website organizationally. Not saying you should use Logan. I'm saying any Albrecht-style lab will work. There's Midwest Lab as well, which is another good Albrecht-style lab. But basically, the way you take the test determines the numbers you get on the report. And so you can't take two different kinds of tests and read them the same way because the numbers mean different things. For those who want to go into the details, let me just give you one example. I'll use the example of phosphorus. Phosphorus is an element that is tested in various different manners. There's the Bray 1, there's the Bray 2, there's the Bray 3, there's the malic, there's all kinds of different acids you use to test phosphorus. UMass, where I went to school, uses what's called the malic 3 analysis on phosphorus, and Logan Labs uses the malic 3 analysis on phosphorus. And and what we did was we split a soil test and sent half of it to UMass and half of it to Logan. And when we got the reports back, Logan said 150 parts per million phosphorus, and UMass said 6.
Yep.
So not sort of close, 150 and 6. Right? That's like a lot. 2,000%? Ballpark? 2,500%? 2,500%. I think. Whatever. It's a big difference.
Any ideas why that would be?
And that's my point. My point is, we like, what? So we called them up. And in conventional ag, in the philosophy of conventional ag, we understand that phosphorus is an anion that ties up readily, and it's difficult to make it soluble. And so UMass figures that 95% of your phosphorus is not available because in conventional systems it's not, and so they just delete it off of your report. There's an algorithm in there which says delete 95% of the phosphorus. Because you don't have life in the soil, and life is the one that actually makes phosphorus available. So people may have heard of mycorrhizal fungi, which is, really cool stuff. Mycorrhizal fungi, cool people. They're really good at solubilizing phosphorus. If you've got a well-functioning biological ecosystem, you don't need to have much phosphorus in the soil because the mycorrhizal fungi will pull what's there and feed it to your plant. Phosphorus gets cycled through and through and through. It doesn't get harvested out really. So, what's that?
There's a lot of non-mycorrhizal.
There are non-mycorrhizal plants, and there are other, species of bacteria and fungi that also solubilize phosphorus. But just simplifying it down to a very rudimentary level, the concept here is that in a conventional system where you apply fungicide and you use tillage, you don't have life in the soil, and therefore these nutrients aren't available, and therefore you need to add fertilizer. Anybody heard of phosphorus leaching and the plumes? Was it Lake Erie that they had to shut the water down in Toledo for a while, or I can't remember who it was. This massive plume, right? In Vermont, you can't apply fertilizer anymore because Lake Champlain has got all these plumes because it's not phosphorus per se, it's the soluble phosphorus that comes in triple superphosphate that you have to add because your fertilizer, because they don't make any money if you don't sell. If you don't buy fertilizer, the fertilizer company doesn't make any money. The fertilizer company is the one that's giving money to the university to make recommendations. You guys know how this works. Everybody know how this works? You know how this works. Okay, so that's the basic broad strokes rationale why I'm going to be recommending not a Land-Grant University soil test, but a Albrecht-style soil test, which means if you've got a Land-Grant University style soil test, it's probably I can't help you with that. Don't take what I'm about to teach you and apply it to your land-grant university soil test. Don't do it. It doesn't work. It's a different, their numbers mean different things. Even though it says boron, even though it says phosphorus, it's coming from a different perspective, and so it's really a different language. That all being said, I'll just sort of run through a few points here that I'd like to talk about. I'm sorry, this has been photocopied a few times, and so it's hard to read, but most of the numbers there, well, we'll deal with them when we get down to them. Exchange capacity is something I want to talk about for a second, then we'll talk about pH. Well, first, sample depth at inches. For those who have never taken a soil test, the process of taking a soil test is one where basically they recommend you go down, you take a core that's 6 inches deep. It's assumed that the 6 inches is the aerobic zone where there's air in the soil, and below that there's no air, so there's no life, and so it doesn't really matter too much what's going on down there. Ideally, you have a deeper aerobic zone, but the general assumption is, if there have to be assumptions, because we're going to be doing math with numbers, you need to set some basic guidelines. The assumption is you're taking a 6-inch deep core. I would suggest you take multiple cores from your field, at least 5 or 6. People ask how big is a field, and it depends on the lay of the land. If the lay of the land is similar across the entire area, you could have a 20-acre field. If it's different, you got high and dry here and low and wet there, you could have, you need 2 soil tests for your backyard, right? It has more to do with the lay of the land, how big your field is, than any, formal set volume. So look at what plants are naturally growing there. If you got similar plants growing in an area, that is probably going to give you a similar, you're probably going to have a similar soil type and mineral levels. You want to take multiple cores, mix them up in a bucket, take a pound out, stick it in your Ziploc bag or whatever, fill the form out and ship it in. Critical piece is you want to make sure that you're checking, if you're doing the Logan test, you want to be checking the box that says base plus or agridine 2. If you download the form off of our website, which gives you the deal price, it's called the consultant price. You know how this works?
Yeah. I have that.
There's like a
also
little
with A&L,
kickback.
If anybody wanted to use A&L, I think Logan may do more.
This is a
More of
special
the
deal. This is a Jerry Bernetti set this up, this test. But generally, they've got the price for the general consumers, and then they've got the price for consultants. And the consultants pay half as much because they give business, right? You know how this works?
Yes.
Right. So what we have is we've got the consultant test form on our website, so you don't have to pay as much. If you go to their website, you're not going to find this. Just saying. So you can do whatever you want. All right.
What about
What's that?
sample?
I was confused by that, going to their site rather than your link.
If you don't go to the link, you're not going to find it because this is not, yes, money.
He's taking conglomerating buying power, so like, that's what I do with
I
A&L. Like,
understand.
if you send
Yeah,
this
he-
sample,
he's
you
got
and
it-
I
he's got it
calculate
now.
On A&L,
Yeah,
you're gonna get a consultant rate, and I just pass that on, so it's a discount.
right.
It's only a 10% that I get A&L, because I don't do a ton of samples.
Yeah.
I just did the Google search instead of
Follow the link on the registration form.
I got the wrong information.
It probably said on the email what to do,
Oh, it did.
and then you didn't listen. Yeah, exactly. Yeah. Why should I trust these characters? They're from up north, anyways. Yeah. All right.
What about on depth of soil testing? I always think it's better to get some more depth so you know what minerals you got down below that the plants can bring up over time.
So it depends entirely on what you're growing. If you've got a perennial polyculture, you probably should be looking down deep. And the question also is, what's your soil compaction? If you've got a plow pan at 6 inches, it doesn't matter what's at 7 inches because your roots can't reach it. You should have a 2-3 foot deep aerobic zone, but most people don't. So what matters is what's there. And then we can talk about the whole conversation about whether you need to add minerals in the first place or whether they're in the subsoil and your plants can bring them up. And if you're growing annuals that have 6-inch deep root zones all the time, nothing's coming up. But if you've got a nice, polyculture with trees and grasses and everything else, then you can have things being cycled up. And then you really should do like a 3-foot soil profile to see what's in your underlying geological material. And you still may not have certain elements, but I am simplifying a really sophisticated conversation down to absolutely rudimentary right now. So understand that. I'm not able to go as deep as I'd like to because I haven't put aside enough time for the conversation.
So if you tilled it, say once or twice this year,
Yeah.
you've already turned the ground.
Yeah,
So, 6 inches is still, at 6 inches, you've already tilled it up. You know what I'm saying?
so it's pretty much universal already, so you don't need to bother with the core.
Right.
Yeah.
Okay.
Plus or minus. Use common sense. Common sense, right? People can tell you something, or you think you heard somebody say something to you, but then your common sense tells you, I don't know. Who do you listen to? People that gone to school, they listen to what they think the teacher told them.
Yep.
People that are farmers, no, they shouldn't really trust anybody if their common sense disagrees with what that person says. Right? As far as I'm concerned, we've got intuition. We're hardwired with the capacity to perceive reality directly through frequency, just like nature does. We'll talk about this later. But that's basically our gut feeling. That's basically what knowing it in your heart means. Because we got antenna systems we're hardwired with. Right? We got antenna in our gut. We got antenna in our heart. And we know about this?
Yes.
Yes. It's totally cool. It's really, really cool. Anyway, so, yes. If common sense disagrees with what you've been told, I would say disagree. Yeah, don't do what you think you've been told. All right. Exchange capacity. I'm not going to have time to finish this whole topic before lunch, but that's okay. Exchange capacity, people may have heard of this concept of exchange capacity. We generally say cation exchange capacity. There is anion exchange capacity. What Logan measures is what's called total exchange capacity, which is the cations and the anions. Anybody who's taken a basic agronomy course or master gardener's course has heard about this whole sand, silt, and clay thing. We know about sand, silt, and clay. So we got our sand here, we got our clay here. We'll just do the sand and clay. The idea here is basically that we have similar volumes of space here and here, but we've got way more surface area here than here. And it's not the sand or the clay that the plant is eating, it's the elements that are attached to the sand or clay. Right?
Well, when they're cellulose.
However the plant gets access to them, it's the elements that are attached to the sand and the clay that the plant is eating, not so much the sand or the clay. And we know what sand and clay are made out of? What are the elements?
Silicon dioxide. And
Silicon, oxygen,
and aluminum.
Aluminum.
Silicate.
and iron. Silicon, oxygen, aluminum, and iron is the vast majority of soil. Silicon, iron, aluminum, and yeah, that's it. So anyway, so we have these elements that are attached to the soil. We got our calcium, we got our magnesium, we got our copper, we got our zinc, etc. So exchange capacity basically is telling you how many of these nutrients are in every unit of space in the soil. So the more surface area you've got, the more capacity you have for the nutrients to be there. Does that make sense? If you have not much surface area, you have not much ability for your soil to hold much. So I like to use the metaphor of a gas tank. Anybody ever rode in a motorcycle?
Yep.
How much gas does a motorcycle gas tank take?
Yeah.
You can buy 10 gallons of gas, and you put that into the motorcycle gas tank, and it'll just end up on the road, right? It can only hold so much. So a sandy soil can only hold so much. The tank is only so big. You can put down all you want, but it doesn't really matter. It can only hold so much. And when the tank's empty, it doesn't need much to fill it. But when you got a clay soil that's empty, it takes a lot more to fill it. So if you ever driven an F-350 or any kind of a decent-sized pickup truck, right, 30 gallons later, you got a full tank. But you can do a lot more work with that full tank of a F-350 than you can with a motorcycle. So a high exchange capacity soil, a clayey soil, can hold more nutrients. It has a greater yield potential, but when the tank is empty, it's takes a lot to fill it up. That's what exchange capacity is in short. I mean, I've got a few basic points here to convey the concept. Is that a question?
You don't have to do it now, but at some point, can you talk about the relationship between biochar and exchange capacity?
I'll put biochar on the list. That's a good topic to have. Yeah.
What's the sort of typical exchange capacity of a real sandy soil?
4, 5, 6. They generally say 8 to 12 is normal, whatever that means. You go out to California, they're all 20, 25, like, oh, really? You go to New England, you got 6s and 7s and 8s. That's why all the farmers left New England.
Why in California so hot?
Because they don't have so much rain, and if you weather the soil over thousands of years, you actually you wear off these bonding sites, and so you've got weathered clays and you've got high energy clays, and so basically because it doesn't rain so much, their soils aren't so weathered, and they've got a larger inherent holding capacity.
Okay.
What has way more holding capacity than clay is organic matter. Right? Organic matter is this fractal structure that's got bonding sites all over the place. And so it doesn't really matter, I don't think, that much what your exchange capacity is. It is what it is. You got your land, you're not going to move. I guess some people do, but generally you've got the land you're working with. You can increase the exchange capacity by building organic matter, which you do by growing healthy plants. Anyway, I don't want to spend a lot of time on this. Just touch on the topic for those who haven't heard of it before. What I do want to talk about is pH, because I think a lot of people consider pH to be important, and I thoroughly don't. And I want to explain why and what pH actually is. So let's just start with a question of what is pH?
Power of the hydrogen ion.
Power of hydrogen. Almost. No. Something about hydrogen.
Measures acidity and bases.
What is acid and base? What is pH? Testing. How much hydrogen there is.
Hydrogen ion and hydroxyl ion.
There we go. It's the inverse log of the hydronium to the hydroxyl ion. Really?
Yes.
I'm going to explain to you. It's real simple. It's real simple. If they understood it, if the teachers understood it, they could explain it to you so you'd understand it. But they don't understand it, so they don't explain it to you so you can understand it, right?
Right.
Right.
You know how this works?
Yes.
No, we don't know how it works. Explain it.
Exactly. No, I don't. You keep telling me it's important, but I don't understand. All right. So we've got this molecule. People have heard of this one.
Yep.
Yep.
HOH, H2O, water. So the concept here is that you've got the water molecule, but you don't really ever usually find a molecule of water, right? You find water together, with multiple molecules together. And the thing about water, one of the things about water, which I do think I understand, is that they say water is bipolar. It's got a positive and a negative pole. And so you have the H's and the OH's are kind of hanging out together, but they're kind of screwing around. Right? And so this H sometimes is hanging out with this OH, and sometimes this H is hanging out with this OH. There's a positive charge and a negative charge, and they're vibrating, and they're never ever really just over here. They're not monogamous, right? They're not. Apparently they're not. So what happens is, depending on the environment, you never have an exact balance of H's and OH's. You have always a few more H's or a few more OH's. It's like musical chairs. There's never quite enough for everybody. And so what pH is, as I understand it, is how many H's you've got to how many OH's. So pH of 7 means you've got 1 H for every 1 OH. That's a perfect balance. Everybody's got a seat in musical chairs. pH of 6 is 10 H's for every 1 OH. It's a log. It's a log. The inverse logarithm. That's a math thing. pH of 5 is 100 H's for every 1 OH. pH of 8 is 1 H for every 10 OHs. People see basically how it works?
So my soil is Lenore, and according to the soil survey, it wants to be 3.4.
Wants to be 3.4. It is 3.4.
In nature, it is, under the trees, it is 3.4.
And that's what we call a thoroughly worn out soil.
That's what I try to grow in.
That's not.
And that's why all the boys that grew up in Appalachia had flat feet and bad teeth, is because their soils that they were growing the food they were eating, which was building their bodies, didn't have in it what their bodies needed to function well. How does this work? What is it? So a pH of 3.4 means you got a hell of a lot of H's. So instead of having zincs and coppers and magnesiums and calciums, you've got H and H and H and H and H and H. You've got a soil that doesn't have any minerals in it. It's got a bunch of hydrogen. Yeah? What happens when the soil life is fed by the plant? I didn't tell them about this, but the plant will make specific food for copper solubilizers if it wants copper, or make specific food for phosphorus solubilizers if it wants phosphorus. So when the plant says I want copper, and it adds amino acids to the sugar to make it food for the copper solubilizers, it injects it down into the soil where it knows where the copper solubilizers are. They go down there, and what they do is they exude acids or bases to solubilize the copper off of the soil, and they eat it. And there's still this charge hanging out here, and so they replace the copper with the hydrogen. And when you do that over and 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 over again, you pull all the minerals out, and you're stuck with a lot of hydrogen, which means you've got a low pH. And the university says, you got low pH, add limestone. Why do they think you want a high pH? Why does the university tell you to have a higher pH?
That's what the plants want.
Why?
Because
So
they're
that the
so
amino
long.
acids work better to.
No, the university does not acknowledge that this happens at all.
Oh, okay.
University, we already went off the reservation with this. This is officially not part of, if you study agronomy 101, maybe you're starting to learn this, but Elaine Ingham was one of the first people who even said this is possible, and that was only a couple decades ago. And people may have heard of Elaine Ingham, but what she's talking about still hasn't made it into the university agronomy protocol, as I understand it.
They relate pH to acid and basic.
Why is it considered to be important? Why
They
is,
give you a chart of nutrients that say they're only available in
Thank
these
you.
pH ranges.
Yes.
Say that again?
They give
I'm
you
gonna
a
draw it
chart
up here
of all
then.
the minerals that plants need, and then they show you the pH scale, and they hone down on the range where most of the minerals are mostly available. Because some of the minerals aren't available at low, but they're not taking into account that the plant has all these microclimates, and the biology creates all these microclimates, and
so,
anyway.
I'm going to draw it up for you. It's the test tube. Got it? Stick figure. I'm really good at stick figures. I got a couple of them. I'm going to put a piece of copper in here. Piece of copper in a test tube full of water. So, in chemistry, in a chemistry set, depending on the pH of the water, the copper is more or less soluble. True, fact. So what she was talking about is there's charts in the agronomy books. If you look at them, and they'll have this, solubility gradient, and they'll say copper is most soluble in this 6.4 to 6.8 range. In a test tube, totally true. A couple things missing here in the test tube. There's no soil, there's no life.
Yeah.
Right? Conventional ag is based on chemistry set experiments. they don't take into consideration that what these soil life do is they raise and lower pH all day long to solubilize nutrients.
In different parts of the root zone, even the same plant during the same day.
Right.
Totally different.
Same spot, in this same spot all day long. You can go from 5 to 7 to 5, up and down, in the same spot based on the acids and bases that the soil life is exuding and to raise and lower the pH to solubilize nutrients. So this biological system is a much more sophisticated feedback loop than the conventional ag system, which is basically a soluble nutrients and solution chemistry set. So we think pH is important because we want the most nutrients to be soluble, and the most nutrients are soluble in this 6.4 to 6.8 range. I went fast through that. I'm thinking a few people didn't quite get it, but
6.4 to 6.8.
is what is generally considered to be the appropriate pH for most crops. But that whole idea is predicated on the thought that there's no life in the soil. And when you understand, I'll just get a little pen here and draw it.
We had some soils that feel like a pH of 4, and we got pretty good crops.
Well, so what's going on? Your pH here
We had microbes.
could be 4.
Yeah,
Your pH here could be 5.
you're taking samples.
But then it'll be 7,
Yep.
and then it'll be 5 again, and this whole thing will happen in 24 hours. What happens in the rhizosphere, in the area where the life is flourishing, is the pH goes up and down all day long because the plant is feeding the soil life, so the soil life can solubilize the nutrients so they can feed the plant. This is the biological system. It's something like 3% of the species of soil life have so far been named. That leaves only 97% we don't even have names for yet. Do you know why we haven't named them yet?
Focus our energy. on
No,
studying.
by our
You can't culture them in a lab.
Yeah.
They won't exist outside of nature. You can't take agar in a petri dish and culture these things. That's not where they live.
You can see it when we put the soil under a microscope.
You can see it when you
different
put a soil on a
ones.
microscope.
Yep.
And you can do now some sophisticated things with DNA.
Yep.
But historically, microbiologists didn't even have names for most of what's underneath our feet because they couldn't study it because they couldn't culture it in a lab. Because it lives in nature, it doesn't live in a lab.
They cultured it in soil for years and thought it was sterile, so
Yeah.
that's why they concluded the chemical approach. But they were culturing at human body temperature with one food, putting a lid on the dish so there's no oxygen. They were culturing for pathogens, basically. So they were saying that these soils have no pathogens before they started.
Well, that's why most of what was found was pathogenic, and which why we considered why we put fungicide in our seed. Instead of putting colostrum on our seed, which gives our plants the ability to establish good, healthy gut flora, we put fungicide in their seed, which kills all their colostrum, which guarantees we're going to have colicky babies. How's that for you? Get colicky babies, they're going to need antibiotics, they're going to need fungicides, they're going to need insecticides because they're sickly. Right? That's the way to set them off wrong. Brilliant. Awesome way to take money from the farmers.
Yeah.
Train them to grow sick plants and then sell them all the products to make them sicker. And you suck all
the
the...
drugs for people.
What I was thinking about all of this business here
Yeah.
is monoculture over a long time will extract specific elements more than others,
Mhm.
and this will increase the likelihood of deficiencies in a profile.
Sure. And it'll decrease the spectrum of species living in the rhizosphere. The more different families of plants you've got, the more gut flora you've got, the broader the spectrum of species. And we'll talk tomorrow about some of the magic things that soil life can do, which violates, as far as I'm concerned, laws of chemistry and not physics. But what life can do is so exciting. It's so, so exciting. Yeah.
So what helpful information is a pH test offering us?
Very little. It basically is telling us how full the tank is. The more hydrogens you've got attached to the soil colloid, the more empty the tank is. And so the lower your pH is, 3.4 means you've got a really empty tank, which means you need to fill your tank. As far as I'm concerned, when I see all these red clay soils down here with no organic matter that are totally tight, I'm like, you guys could so do with a few minerals. You could so do with a few minerals. And if you got pastures and you can't afford it per acre, I understand that. But if you're growing vegetables, you could really, really benefit from a few minerals. I grew up on an organic farm. We didn't talk about minerals. No one told me about this stuff. We had pests and diseases year after year after year. We struggled to make a living. I filled the tank with minerals, and now my crop yields are dramatically higher. My pest pressure is down. My disease pressure is down. My flavor, my shelf life is up. My marketability, my bottom line economics, my time off, all improved. And this is what, east of the Mississippi where we get lots of rain, we've got weathered soils. And down here, you guys didn't get glaciation recently. So your soils are even more weathered. The last time you got new minerals distributed by nature was a long time ago. As I understand it, there's this ridge that goes across, about a third of the way up in Iowa, and I-40 passes through just next to that. And all the land north of there is worth 20 grand an acre, and all the land south of there is worth 12 grand an acre. And what that ridge is where the glacier stopped.
Glaciers never came down here
That's my point.
at all.
And that's why you got a pH of 3.4, is because the soil, it's been raining, 40, 50 inches a year for the past how many 100,000 years?
Billion years.
What's that?
About a billion years.
Since the last glaciation occurred?
California and the Great Lakes have been up and down 19 times,
Yeah,
and we've been up once.
up once. So I don't want to sound like a northerner and make comments about southerners, but I'll just say your soils are really, really weathered. They're really, really, really weathered, and that means their tank is empty, which means they don't have a lot to put into the plant, right? Which means there's not a lot to put into your body, right? I mean, it's real simple, and we're going to talk about how to address this, right? I mean, we have to break for lunch at some point, but nature does this with rocks. Like I said, the Nile River does this with crushed up rocks from the glaciers crushing up the rocks. This is what the Ganges River does. Is it crushes up rocks and spreads them on the land. Right? That's all you need. Those are the basic ingredients you need to build up soil, are these basic elements that are in rocks. So I'm not saying you need to spend lots of money on fancy fertilizer. If we mimic nature, if we see how nature does it, we can actually systemically really improve things with really little bit of money, with a really small amount of money. This is what's going on in India. This is why the land is so weathered and weak. In Africa, we've got major places where there hasn't been glaciation recently. They don't have the alluvial plains, and volcanism doesn't. I mean, volcanism is your other option. Volcanoes blowing up, right? Mount St. Helens.
Yeah.
That's your other option for remineralization. And on a different kind of time scale, sure, nature will revitalize the planet. But if you're talking about a human time scale, if I'm raising kids and I've got worn out New England farmland, it's really important to me to put the minerals down now, because I want those minerals in my kids' bones when they're young. I don't want to wait 20 years for nature to figure it out slowly through bioaccumulator plants and things like that. Anyway, I didn't want to spend too much time on these topics, but I think they're important to cover. Yes?
I just want to try and say a couple things and then get you to revise them.
Go for it, please.
So, taking a pH test from a soil that's been abused or not used or neglected will give you a certain amount of information, but it might not actually tell you what minerals are present, because the biology might not be active enough to give you
to release them.
in plant available form. So that's one thing I'd like to use, proper commentary on. And then the other thing is, two of the ways in which you could alter the pH would be to simply put out the food for the microorganisms to feed the bacteria and fungi to start stimulating things, and that would potentially change it as well. But also simply just putting, like if you were to install or introduce a perennial polyculture, then the plants would begin altering the pH themselves, right?
Gotta make sure I'm not using the wrong pen on the wrong board here.
There's three things there, I guess.
You got your clay. You got your bonding sites. Low pH means You got all hydrogens there. That means you don't have the calcium to release in the first place. So sure, there is stuff locked up in here. Sure, if you take a mining assay and you dissolve the entire soil, right? So what the Albrecht-style soil test does is tells you what's reasonably releasable through biological activity. It's not perfect. There's no perfect soil test, but it's not, the Albrecht soil test is not telling you what's available right now. It's what can life reasonably release, as I understand it. If you dissolve the whole soil entirely with a very strong acid, you will find boron in here. You will find cobalt in here. You will find calcium in here. But it's not reasonably easily released. So my critique of the soil food web model is that if you don't have a bunch of minerals relatively available in the first place, you don't have the food for the soil life to eat. So I didn't talk about
It's
minerals.
true.
Minerals, it's true.
I'm just
She
saying.
spent tens of thousands of dollars.
More soil than anyone in the U.S. over lots thousands of acres and doing a lot of this work and putting out microbes like crazy. Minerals will limit the microbes because they're going to harvest them
M&Ms,
first, and it's only when
microbes
they
and
grow
minerals.
That they die that they plants are fed. So
Microbes are found, I mean, it's the life,
how you get the minerals?
it's a
is
living
one
system,
way,
so we
but-
understand the critical importance of life. However, minerals are foundational. I like to use the example of vitamin B12. Vitamin B12, people have heard about vitamin B12. If you're a vegetarian, so I've been told, sometimes your doctor will tell you that you need to supplement your diet with vitamin B12 because there's not enough in your plant-based diet. There's not enough vitamin B12 for you to function. B12 in science names is cyanocobalamin. Cyanocobalamin basically means one atom of cobalt with a few amino acids attached to it. So it's not the amino acids that are the limiting factor, it's the cobalt that's the limiting factor. So if you don't have enough vitamin B12, you become anemic. You become weak. You have low energy. You're just, right? We know vegetarians,
Yes.
stereotypes,
No.
vegetarian, no
It
stereotypes.
happens.
It's not a stereotype,
It happens
it's
to a lot of
true.
people. Yeah.
Stereotypes are true. Not always, but a lot. When you really don't have enough vitamin B12, you know what happens? You become dead, right? You don't need much vitamin B12, which is really cobalt. You don't need a lot. You need a really small amount. But if you don't have enough, you're dead. End of conversation. Exactly the same for microbes, right? 80% of the 3.5 million species of microbes are B12 dependent. You don't have enough cobalt in the soil, they're dead. What I like to say is, if you were to take 2 airliners full of humans and drop them off in Alaska because you wanted to inoculate humans into the environment where there's no humans, they're mostly going to die, right? They don't have the critical components necessary to live in that environment. That environment is inhospitable for them. So you can keep dropping them off. You can keep applying compost teas, and you apply more compost teas, and they're alive for a little while, and they start to build buildings, and then and the next time that you drop some more off, maybe they find the buildings that are halfway built, and they get them established, or the garden that got planted, but they died before the garden came to fruition. And so only adding inoculants without balancing the minerals as well, to me, is it's a silver bullet strategy. It's saying it's all microbes, which is no, microbes are really important, but you also need minerals, you also need air, you also need water, you also need organic matter. If you don't see the whole process as a living ecosystem and make sure that all the pieces are present, you're not looking at it honestly and dispassionately. So it is true that we have plants that are called bioaccumulator plants. And it is true, I mean, you can, the best way to get rid of dandelions is to add limestone, right? I mean, dandelions are a calcium bioaccumulator, and when you've got enough calcium in the soil, they'll go away. All these different plants we've got the docks, we've got the thistles, all these, the things we call weeds that people come in and try to kill with their herbicides. Those are nature's way of balancing minerals. So they are bioaccumulators of different elements, and they'll grow for a couple generations or 10 years until the minerals that they are bioaccumulators of are present in sufficient levels, and then they'll die off, and the next families of plants will come through. That's the way nature balances their soils, in between the ice ages, as I understand it. The question is, are they just pulling minerals out of the subsoil or something else going on? Because I'm aware of research where people did something like they took nettle, which is considered to be a boron bioaccumulator, and planted nettle in a pot of potting soil that didn't have any boron in it, and grew the nettle, and then tested the nettle after it grew and found the boron in the plant, even though it wasn't in the potting soil, and there was no subsoil for it to be bioaccumulating from. So, yes, there was boron in the nettle, and no, it did not come from the soil.
They did a grinding combustion on the soil.
I think so. Yeah. So Jerry Benetti told me this story. I don't know. I didn't track down all the details. This is a great one to test.
Because the boron's in every cell, so if there was soil, it's, like you said, it's in there, but it
It's
might not have been in the
potting
in the
soil or
stable,
whatever.
ready to go state.
There's all kinds of things you can do. I mean, it's leading towards this topic, which is, the formal term is biological transmutation, which you can test in many other ways as well. Anyway,
So isn't there,
on my agenda for tomorrow, but
So microbes with minerals work better, like we started adding.
M&Ms. You know what M&Ms are? Microbes and minerals. Microbes and minerals.
enzymes.
Microbes and minerals.
So if you add
If you don't have
enzymes-
microbes and minerals, you're out of luck. As far as I'm concerned, you have to do both. You can't just do one. You can't just do minerals. You can't just do microbes. You need to understand where you're at in the balancing act.
so is that nettle story defying the law of entropy?
I'm going to talk about it tomorrow. It's on my agenda for tomorrow. It just came up as part of this conversation in relation to bioaccumulator plants. To answer, my truth is there's a lot more going on there than we understand. And we have data that tells us there's a lot more going on there than we understand. Good, proper scientists have documented it over and over again in lots of different cases, and we don't like to talk about it because it doesn't fit with what we learned in science. But I was watching, we homeschool our kids, and we have a tutor comes, and she was talking to the kids about brains, and the brains on Thursday. That was her. She made a little brain cap, and then we had the different parts of the brain and what happens in this part, what happens in that part. And she was telling the kids about memories being in the brain, stored, and I know they're not stored in the brain. I've got 3 cousins that are PhD neuroscientists, and I ask my cousin Audrey when she comes to Thanksgiving every year, Audrey, have you guys found memories yet? And she has to say no, because they haven't.
They're stored in cells.
Well, where they're stored is a really interesting conversation. That's where I'm going with it, is the field. Because we think they're stored like information stored on a computer hard drive with ones and zeros, and they're not. They're not stored in your brain. Memories are not stored in your brain. That's what neuroscientists will tell you, even though you learn in school that they are. Right? So what's the cutting edge science has figured out won't get into school for 50 years. And so we're still trained about this stuff. So we are not trained about biological transmutation, even though it's good, solid literature that's decades old at this point. I really do need to break for lunch.
This is a good time to refill our brains.
I need to break for lunch. I haven't gotten anywhere near as far as I want to on this topic,
Dan,
but
can I get you to clarify
I think
one
that's fine.
thing on-
I will clarify one thing and then I want to break for lunch.
All right.
Yes.
I heard you say 80% of soil microorganisms are dependent
Are
on B12.
B12
You mean
dependent.
they're dependent on cobalt to make B12, or they're dependent on B12 that they're
They need
sourcing from some other place?
B12 to function biochemically,
So they're-
and cobalt is
So they're
part-
dependent on cobalt
they're cobalt dependent
to
organisms.
make B12.
Yes,
Okay.
you can't have B12 without cobalt.
Okay, all right.
Yes, they're cobalt dependent organisms. All right.
I have a couple of things
Announcements?
about